Okay, so up next we actually have a collaborative group. We have Geotech and hydraulics, so it fits in perfectly with what Paul and Laura have been talking about. First up is Daniel Alzemora. He's a senior geotechnical engineer with Federal Highways Resource Center. He's also the geotechnical lead for the Resource Center. He's a professional engineer in the state of Georgia, over 32 years of geotechnical experience, 12 of that being with private practice, 20 years being with Federal Highway Administration. Has a Bachelor of Science from University of Connecticut and a Master of Science from the University of Colorado. So with that, please welcome Daniel.
Well, thanks for allowing me to give you just a few words on geotechnical engineering for hydraulics and inviting me to participate here. By the way, I have learned a lot in these last day and a half, and it's been wonderful to be here. Before I get started here, I want to go back to Laura's slide. Where'd it go? Oh, did you close it? Oh, there it is. This slide, I think, there's 3 or 4 spots in here, and I'm going to be talking about geotech and hydraulics and communications between us. And I think this is a great start to the discussion that we're going to have here in my presentation. But this flow chart here, where there's plenty of opportunities for us to communicate better and to interact with each other, I think will give us a much better design in the long run. Anyway, thanks, Laura, for having that one. Where am I? I'm just going to go like this. Hopefully now I'm not messed up. This one. Go. All right. So what I wanted to do here is to talk about communications and interactions between our disciplines. And I misstated, I think, this miscommunication. I think it's more not enough communications and I think we could do better. We want to be able to understand from a geotechnical perspective, we just don't know what the needs of hydraulics are. So that's an opportunity, right? We don't know where the information is needed at the surface, at different locations where we might normally investigate. We also understand that you guys don't know necessarily what some of the capabilities that we might have to investigate these sites are, and what some of the limitations are for us to be able to get out to some of these locations and get the information. So that back and forth communications is important. So I wanted to see if there's a way to develop some paths of communication in earlier phases of the project development process, and in the planning of the geotechnical investigation and the assessments of the Scour analysis that you guys are going to be doing. And you've probably seen slides like this before, and we're going to talk a little bit more about that in the next presentation with Cornell and James. But what we want to do with this next Scour is try to look at both sides of this equation. There's the load side of the equation, which is the hydraulic forces that are being generated by the moving water, and the resistance side of the equation, which is the resistance of the soil to that erosion force. And that's the part where the geotechnical component comes in, is can we develop a way to give you that resistance for the soil so it doesn't erode as quick, or give you those properties that you can use to design. So just my current understanding of practice and of your practice, of the hydraulic engineering practice. First of all, erosion is a function of both soil and water. But soil is a large component of what is happening. So sand erodes much differently than clay, for example, and rock. In most cases, Scour is evaluated based on the D50 of the soil at the stream bed. And that's my understanding of how normal practice occurs. And for non-cohesive soils, the minimum D50 that you could use is 0.2 millimeters, right? What happens, and we assume, at least my understanding, is that this material is infinitely deep, right? It just continues on forever and ever. So there is an opportunity here for us to interact and take advantage of the site investigation that's already occurring in our geotechnical engineering practice to develop the foundation design of these bridges. So when we do a site investigation, our primary objectives are to define the stratigraphy of that site so that we can figure out what is underneath and what are the resistances that we can use to come up with the foundation design, right? We need to know if it's soil, if it's rock, and what are those strengths of those materials and how it will behave under the loading that we're going to be applying to it. We want to identify and address any risk associated with that those subsurface conditions, and we want to define the conditions that impact performance. For Scour, there is a need for geotechnical information in order to do the Scour calculations. Scour is a risk to be considered at the site, right? Scour is one of those risk factors that we need to think about. And Scour is a condition that impacts performance of structures. So in all of these areas, that the objective of geotechnical subsurface investigations, Scour calculations fit right into what we do. So a geotechnical site investigation, consists of the following items, right? So we need to understand what the project needs are. Great opportunity for us to figure out incorporate the needs from hydraulics into that understanding. We develop a site investigation plan, and then we conduct we act on that plan and collect the information that we need, through borings and in situ tests, geophysics, collect samples, and then we test samples. And then we summarize all this data and do the interpretation of this data so that we could do the design of that foundation. You've probably seen some borings before. We collect SPT samples with split spoon samples and Shelby tubes to collect the different types of material so that we could test them in the lab in the future and kind of get a feel of what the material is when we pull it out, right? So get an idea of the behavior of that material. We also have many other types of in situ tests like CPT that gives us a much higher resolution of the data with depth. An SPT, a boring, like we traditionally do, we collect samples typically every 5 feet. So we only know information every 5 feet, and we know about 18 inches or 12 inches of materials, really, in those 5 feet. With a CPT, we're collecting samples every inch or something like that, through data, not necessarily physical samples, but we're collecting data that we interpret into soil behavior characteristics, which gives us much better information. So it's a really good tool that we can use to collect information. And it could be much quicker. We can do probably 3 or 4 CPTs in the same time we could do 1 SPT. So we can collect samples much quicker, so we can do more frequent testing. We could also do some geophysics. And that's a technique that you There's several different techniques, and I'm not going to get into the details of this because way too complicated and we don't have enough time. But we could get a better understanding of what's underneath in the subsurface and to give us a better interpretation of what was happening in between those borings. We're collecting borings maybe every 100 feet in an embankment, maybe one at every foundation element at the abutments and the piers, but we don't know what's happening in between, right? We really don't have any data there. We're making some interpretations, and we're making the best judgment, engineering judgment, based on the geology that we have of what is in between those borings. With geophysics and the physical borings and the physical data that we collect, we can calibrate the geophysical information to give us a much better profile along in the foundations, to give us a more continuous sampling of the subsurface. So then we do a whole bunch of tests, and I'm going to focus in on only one area of this because I think it's more relevant to what you guys normally do, which is material classification. What type of materials we have. And generally speaking, we're talking about gradation and Atterberg limits. And then we use this information, so we take our samples, we run gradations, and we do our Atterberg limits, our plastic limit, and our liquid limit, and calculate our plastic index. And then we use that information to classify that material as a silty sand, a sandy silt, a sandy clay, whatever that might be, right? And we have different ways of classifying it. We have an AASHTO classification system or a unified soil classification system. Different states use different systems. Some states use both. Some states use the AASHTO classifications for pavement type applications and the unified soil classifications for geotechnical applications. But at the end of the day, this gives us a soil behavior, kind of an idea of the soil behavior of the materials that we're seeing. So now I want to even narrow this down a little bit more for this discussion, which is on the gradation, because it's what you generally, my understanding of what you generally use, which is the D50, right? So here's some 4 samples from a project in North Carolina. And this particular project has 2 different types of materials, right? You'll see in this curve, oops, sorry, hit the wrong button. You see very different material gradations here. So what does that mean, right? We know that our definition of fine-grained materials or silts and clays are at 0.075 millimeters, okay? So that's basically the boundary of what we defined as cohesive materials or fine-grained materials and granular materials. This value here is the D50, okay? So wherever those curves intersect that line, that's the D50 that you normally would use. 0.2 millimeters is the minimum value that you would use for the typical equations to come up with your scour depth for granular materials, right? For these materials here, which are sandy materials, sandy with some fine gravels in it, you would use something in the order of 0.38 millimeters, not a 0.2. And that gives you a significantly different resistance, right? I'm assuming. I haven't done the scour calculations, but I would assume that would give you a different answer than if you would use 0.2 millimeters. This one is several orders of magnitude smaller, right? What do we do with this material if we don't have critical shear strengths of these materials? My understanding is that you resort to going to 0.2 millimeters. This material behaves very differently than a material that has 0.2 millimeters. There is nothing similar about these materials. So when we make these assumptions, we are taking a totally different interpretation of what we actually have in our subsurface conditions, okay? So just just a summary of that. And basically what I want to say, the alternative is that you would go out and get some Shelby tube samples of that clay material, run some EFA or ESTD tests or whatever other erosion tests that Cornell and James are going to talk about here in a little bit, and get that critical shear strength of that material so that then we can use what's already, we could already do this in HEC 18 using this section 6.7, right? That allows you to use a cohesive material with the critical shear strength in our analysis. But my understanding is we don't do that very often, all right? And usually this happens way too late and you don't have this information, so you have to resort to that D50 of 0.2 millimeters. Opportunities to communicate early on so that we can collect those Shelby tubes, send those samples out early, you have that critical shear strength available to you, and you can then consider that, at least, in your evaluation of Scour, if it makes sense for that project. We're already out there doing the borings. It doesn't take any additional effort or very minimal amount of effort because we've already mobilized to the site. We have the people on the site. We have the equipment on the site. Collecting a few extra Shelby tubes is not a big deal. Opportunity. From all that information, we throw all that together, boring, CPTs, geophysics, and then we come up with some sort of interpretation of that subsurface condition that we use for our design purposes. It wouldn't be very difficult to add in here information that is relevant to you for your Scour calculations, right? It would be very easy to do that. And to finish up here, I'm probably long on time. I'm good. Just to summarize this is, I wanted just to give you guys an idea of the opportunities that we have in communicating a little bit more and having that discussion early on with a multidisciplinary team, your bridge folks, the geotechs and hydraulics. Here's our project. We have these old borings from when this bridge was built. There's a clay layer 10 feet down, and we might be able to get information from that clay layer that can help us in our Scour calculations. Let's collect some Shelby tubes. Let's run some tests. Let's see if it works. If it doesn't work, you haven't lost anything. So, just that communication early on to get that opportunity would be very helpful. I'm not going to read all of this, but I'm going to give the same message here that I'm communicating here to the geotechnical folks in the opposite direction. Let's talk to you guys. So if you start hearing from your geotechnical counterparts at your DOTs, hey, let's talk about what you need for this particular bridge. Let's have that communication. Let's see if we can help each other to improve our designs. And I won't bother you with the dinosaur that Joe talked about earlier. But are there any questions for me?
Does the Federal Highway Resource Center have any plans for establishing those best practices or encouraging those best practices in the geotechnical design community? Because we're usually, unfortunately, we're commonly downstream of that evaluation, and it requires the borings for us to say, hey, it looks like there's this giant clay layer, and then they've already demoed and done their analysis.
Right.
So this is something that happens real early on. And ideally would be identified by the geotechs during their field evaluation, so they collect that information.
We haven't had that discussion as far as developing those guidelines. Okay, that's for sure. I think as you start getting these projects in hand, at least initially, I don't have guidance for you right now, but having that, you get this project, call, your geotechnical engineer and say, hey, we have this project. they're probably seeing it as well to start programming their investigation early on. Let's see if we can go and get some information, or do you think that you have some old information, old borings from a previous project that we can take a look at and start from there? We always start from, as a geotechnical engineer, we always start from what information that we already have, from the previous project, or from whatever other sources are available. There may be enough information there to get started.
What a competent non-scourable rock as related to rock quality designation percentages. There was clear guidance in the previous version of AKT about that kind of went away in the current version of AKT. Is there any plans to bring back RQD
Scott, I don't know
guidance?
if you.
You're talking about information from previous versions that was
Yeah,
eliminated?
the version 5 AKT does not mention even RQD as an indicator of whether a rock is scourable or not.
It covers rock scouring. I'm not sure if I'm
Yeah, but
understanding.
there was a table that said RQD bigger than 70%,
Yeah.
dealing with
There used to be
non-scourable bigger
there
than
was something
50%.
Jerry DiMaggio made back after Scour, and it was essentially a table of RQD. But when you consider the glacial till at Scour itself had an RQD of 90 or 95, basically the concern was that that is not, again, that's when we need to talk to the geotech to say that that material may have a certain characteristic that makes sense, but is it going to be applicable to what are the courses that are being exerted on it during a Scour event? And so that's why it's not related, that's why we did kind of meld that into FHWA under talking about geotechnical considerations. So I hear what you're saying. It's someplace where, when we're updating, as Paul talked about FHWA, we can go back, talk to the geotechs, talk to people like yourselves, and revisit that. But what we were scared about was that people were taking the RTD without the context of what that geotechnical, the soil strength material behavior can be, and taking a false sense of security about how it was behaving for a given site. Granted, I'm not worried about it. I got him. But something that's more problematic, that's when we started getting concerned. So that's,
And RQD on its own probably is not the only parameter that you want to look at. So, there's different aspects of rock that you need to consider. There's more, rock is probably more complex than the soil. It may be more resistant, but it's much more complex to analyze and to see the resistance that you have. Okay, so I think it's something that we probably need to work on some more in order. But right now, what Cornell and James are going to talk about is more of on the cohesive soil side, not on the soil component, not getting into that rock the rock resistance.
but we definitely hear you.
Yeah,
I would add too, for the point of the question about the framework for the collaboration, WashDOT actually just did have the design manual will be updated here shortly. It'll be approved, and there is a new flow chart for the coordination with geotech, hydraulics, and structures, starting at the scoping level all the way through design. So I'd encourage you to look at that. But big hand for Daniel. Thank you, Daniel.